Thank you. Good evening. Can you hear me? Everybody here? Before I get started, I'd like to thank Eric Ward and the staff of the library. Just had a phenomenal day here. I got a great tour of the library. I'd like to thank the Board of Trustees and everybody associated with the library. You should be very proud of this library that you have here in Kansas City. I was a trajectory specialist at one time in my career, and today I got to see the books from Kepler and Copernicus and Isaac Newton, and so I can't probably explain in words what that treat was like for me to see those books. I learned the theory in engineering school. I've applied the theory in my career at NASA, but just seeing those books. So before I get started, I'd like you guys to give a round of applause to the staff here at the library. I told Eric that, instead of doing my day job, I probably would just like to come here and spend, a week wandering around if they'd let me roam, but I don't think NASA would probably allow that. So I want to talk to you tonight about the Asteroid Redirect Mission, and I think this illustration probably sums it up the best. If you think about an American and an international partner astronaut, perhaps, exploring this boulder, which has been moved from its native place on an asteroid into this lunar vicinity in what we call a distant retrograde orbit, and we would then use Orion as the sole spacecraft for those two astronauts to do a couple of spacewalks to extract samples. And think about this, 71,000 kilometers from the moon, further than humans have ever gone before. We think this is a pretty exciting mission for NASA and a pretty compelling early use of Orion and SLS. So what I'm going to do tonight is sort of take you through how we view exploration. I'm going to talk to you a little bit about, in addition to the Asteroid Redirect Mission, I'm going to talk about Orion and SLS and the International Space Station and give you a sense of what's going on there. And then we'll talk in detail about the Asteroid Redirect Mission. This is kind of the way we see exploration in a simplistic model. We have three regions of space. We call it the Earth-reliant region, and that's where the International Space Station flies today. The proving ground, where we'll do this Asteroid Redirect Mission out in what we call cislunar space, a vicinity around the moon, and then someday the horizon destination is Mars, where we call that an Earth-independent region. And the reason we talk about it that way, if you think about the space station today, the crew could come home in a matter of hours if they had to. If there was an emergency, they can get in the Soyuz vehicle or very soon a U.S. commercial vehicle and come home if they had to. The delay time in talking to mission control, there's really no delay time essentially. So we can command the space station. So it's a way to get supplies to the space station very easily. As we move further and further out in space, that is going to become more problematic. For example, the time delay at Mars is somewhere between 5 and 20 minutes. So think about trying to have a conversation with somebody, 5 or 20 minute delay. I mean, we get irritated when there's a delay in the cell phone. So we've got to think about operations dramatically differently. So the crew will have to get a plan and execute that plan and essentially text message back and forth with some delay or send videos back and forth. So how do we make this transition from this Earth-independent regime from the Earth-reliant regime where we're at today? And I spent 25 years of my career on Space Shuttle and Space Station working in this regime. And I can tell you as a flight director, the thought of a 6 to 9 month journey to Mars and the crew being on their way and dealing with contingencies, it's hard to comprehend. So what we've come up with is this proving ground region of space where we'll do missions around the moon, and the delay time to come back to Earth the delay time is on the order of 3 seconds for communications, and it may be 10 days from Earth for the crew to come back in the Orion. So this is sort of a staging ground to do missions as we move out someday to Mars. So I'm going to start talking about a few things going on that I'm sure you've heard of, but I will share a little bit of information with you. How many people have heard of the one-year increment? Several hands. Okay, great. So in March, we launched Scott Kelly and Michael Kornienko to the space station for a one-year mission. And the idea behind this mission is we're really trying to collect data for the journey to Mars. We have most of our increments, we call them expeditions or increments, last about 6 months. That's a long time to spend in space with maybe 6 of your friends. Imagine a 3-bedroom, 4-bedroom house, 6 months, and you're not leaving at all, except maybe to do a spacewalk. So these two gentlemen will stay on the space station for a year, and what we're trying to do is understand how the human body responds in space at that time frame. We don't know if there's some magical cliff. The body seems to do very well in space. It seems to, within a few days, to kind of get used to zero G, get used to the fact there's no gravity. But we're looking at the health effects. So we're really looking at bone density, bone strength, aerobic capacity. They're going to get poked and prodded, and they're going to get various samples taken, and some of those returned to the ground to try to study how the body is responding. We have many of these long-duration spaceflight things solved by exercise and diet. Those are the two things that we found in space that really help keep the human being alive. Crews need to exercise a couple hours a day, and they need to eat a very good diet to get the minerals they need. And so it's probably good advice for all of us, actually. We've encountered a vision issue relative to the astronauts' vision. Some people end up coming back with their vision not being as good as it was when they left. We don't really understand this, and so we're working on understanding that for this 1-year increment. And then, of course, you see at the bottom of the slide, retired astronaut Mark Kelly and Scott Kelly. They're identical twins, so they have very close to the same DNA. Mark's on the ground, Scott will be in orbit for a year, and so there's a big study to understand the DNA changes over that time frame. So this is a big mission for us, and over the next year, a lot of the crew time on the space station will be spent with this 1-year increment. This just shows astronaut Michael Hopkins. He's using this device to measure the intracranial pressure to try to understand, is it related to the carbon dioxide levels are a little higher on the space station than they are on the ground? So we're doing a lot of different studies. Fluid shift in space is another important studies. And this research on space station, the reason I'm talking to you about space station is because it's really connected to exploration. It's a great platform, it's a great laboratory to do this kind of research. Also on the space station, we are looking at various kinds of life support systems. So on the space station today, we reclaim about 72% of the water. So that means that we're recycling the urine, we're recovering condensate from the air when the crew exercises and they sweat. It goes into the air. We take that out of the air and recycle that water, and we purify that water. And the water that comes out of the life support system is as pure as any water you'll ever drink here on Earth. But it's important for the steps to go to Mars. We know we can't take everything with us. We know we have to break that bond with Earth. And so this is something we do on the International Space Station. We're flying a lot of different experiments to understand exploration in terms of systems. We are flying rendezvous sensors. We'll fly a docking system for commercial crew vehicles on space station that we'll use for deep space. We'll test spacesuits on the International Space Station that we'll use for deep space. So we see the space station as a great place to test these systems. And the primary reason for that is it's relatively easy to get things back and forth from Earth to the space station. And then we also see the space station as a place to establish a commercial market in LEO. And so you see here on the top, you see the Bigelow module. That's going to fly up on a SpaceX vehicle. It'll fly up there's a trunk, think of it as a cargo compartment, and it's almost like a pickup truck where we can use the robotic arm that you see here. We can grab it out of the trunk and put this on the space station. And we're testing this inflatable technology. This is a technology that NASA prototyped and built in the 1990 timeframe. We licensed it to Bigelow, and now he's sort of pioneered these inflatable modules, so that'll be a great test. We have 2 cargo resupply vehicles that are commercial. We have the orbital Cygnus vehicle that will fly again in October, and then the SpaceX Dragon. They've flown twice already this year for us delivering supplies. They'll fly again in the June timeframe. And then we have various CubeSats that we launch out of the space station. We can take these CubeSats up in these cargo vehicles and launch them out of the Japanese airlock on this device. And so we see the space station as a place to start a little bit of commercial research as well, with various medical companies and drug companies are actually flying experiments up to the space station. We're studying viruses in the microgravity environment. We're studying lots of things in microgravity. And so we see space stations sort of evolving as a commercial entity in space. Also, if you think about the space station, it's pretty incredible. We've had a human being in space continuously now for 14 years on the space station. Not the same human, but we've had an American and a Russian in space for 14 years. And if you think about, there's a lot of people that have been born that have never known a time when an astronaut has not been in space. And so we're starting to understand, I think spaceflight in some ways might be becoming more routine, and a lot of people might be thinking that it's pretty normal to live in space, which it's actually not that normal. So a little bit about the commercial vehicles. I got a question before the talk. We have two. We just awarded last year two contracts to two companies, to Boeing and SpaceX. This is the Boeing system. This is called the CST-100 capsule. So NASA's embarked on a little different strategy relative to how we contract for the cargo vehicles that I talked about. We only pay for goods delivered. So it's a service. We don't own those vehicles. So we have to make an investment prior to each flight. But if the goods aren't delivered, then NASA doesn't pay for it. It's a little bit better way to... Industry is so far advanced compared to where they were in the early days. We can embark upon these new things. In crew delivery, we're going to try a little different technique where we'll let these companies own these vehicles, and we'll contract with them for the seats to take the crew to the space station. The important thing about the commercial vehicles, it'll allow us to expand the space station. Today we have 6 people continuously living on the space station. We'll get to add another American crew member, a 7th crew member. That may be an American or a European, depending on the increment. And so we'll be able to increase the amount of research that we have on space station. Boeing already has started doing a lot of testing on their spacecraft at White Sands and the propulsion system. They're building a launch escape tower. This is Complex 40 at the Kennedy Space Center. They're building a launch escape tower. They've already started that work, and they're making a lot of progress. The other company you've probably heard of is SpaceX. They've launched, I think they've launched a total of 5 rockets this year, 2 of them for NASA to the space station. Recently, last week, you can see over on the right, they did their pad abort test. And so this was an important test using specialized engines on a derivative of the vehicle that they use. This is their cargo vehicle. This is their crewed vehicle. They did a test from their launch complex. It probably took about a minute to go out. This is in the case on the top of the vehicle. The crew would be in there if there were an emergency. They could blast off of the rocket and get clear and land in the water, and this test was an important demonstration for them. One interesting thing about these commercial companies is we work hand in hand with them. The parachute system that we use for these companies are very similar to what's used for Orion, so we share data back and forth with these commercial companies. We're also learning from SpaceX. They're trying to recover their first stage of their rocket, this stage. Elon Musk has this idea of reusing this stage, and if you've watched videos, he's trying to fly it back to a barge. That's important for us. For going to Mars, the same kind of trajectory that's required, flying backwards into your plume, we're learning from this as well. And we have a NASA team at JSC and a cross-agency team working with them. So this is just a little bit of what's going on in Space Station. I thought I would share it with you since I'm here. And of course, at the end, once I'm concluded with my talk, I'll take any questions. And then now if we turn to exploration, we are embarking upon ultimately to build this Space Launch System rocket, which will fly with crew in 2021 and using an Orion spacecraft, which is much bigger than the Apollo spacecraft. It lands at about 19,000 pounds. So we have a sequence. We did a pad abort test out in New Mexico back in 2010. I'll talk more about the Exploration Flight Test 1 in December. How many people watched that test flight? So we have a few people that actually saw that. It was pretty big deal for us. First time we've tested a spacecraft, a human spacecraft, way beyond low Earth orbit since the Apollo time frame. We'll fly this first version of the Space Launch System on a mission called EM-1. This will be an unmanned test flight, and we're already starting to make the hardware for that flight. We'll do an ascent abort test. We call it AA2 or ascent abort 2 in 2019, and leading to this first crewed configuration of the Space Launch System. So we're pretty excited about this, and I'll talk a little bit more about this as we move forward. I think a lot of people don't understand what's going on sometimes behind the scenes. We're in the middle of a lot of testing to get these rockets ready to go fly. So we'll talk about EFT-1 in a little bit. We're starting to test the engines for that Space Launch System, the big rocket that we'll use to do the Asteroid Redirect Mission and also to go to Mars. These are shuttle-derived engines, but they have a little bit different conditions required for the flight. So we're testing those at the Stennis Space Center. We've already delivered some of the advanced controllers. We have 16 engines left over from Space Shuttle that we'll use for these early flights. And then we started building the sections for these big barrel sections. This is where the fuel is stored. There's 7 total required, 5 for the liquid hydrogen tank and 2 for the liquid oxygen tank. We've started building these barrel sections, and they'll go into test later on at the Marshall Space Flight Center. So we started to put real hardware together. This work is occurring in New Orleans at the Michoud Assembly Facility. And then recently, back in March, we had a big solid rocket motor test that's important for us out in Utah. This is at Promontory, Utah. And this was testing this big 5-segment rocket motor, which is a derivative of the shuttle solid rocket motor. And so we did that test. This was a cold booster kind of configuration to understand its performance. We'll do 3 of these qual motors to get ready for the first exploration mission 1. So this is real hardware, real testing happening all over the country. And then I'll talk a little bit about the Orion spacecraft, which we're going to use to take the crew to the asteroid. So this just shows you some of the hardware. So it looks a lot like Apollo. There's a crew module. This is a crew module down at the Kennedy Space Center in assembly for that Exploration Flight Test 1 mission. It has a service module. This was a dummy service module for that flight. The service module will be built by ESA for the first 2 flights. And so we already have started a partnership for exploration with our international partners. And they're going to take a vehicle they call their automated transfer vehicle. They used to bring supplies to the space station with this vehicle. They're going to modify that, and we'll use it for exploration mission 1 and all subsequent missions. And then this is just the size of the upper stage that will be used on EM-1. This is the same stage used for the Delta IV Heavy today, and so it's a big, huge stage. And then this is a view from the top of Orion with the launch abort system on top. The launch abort system is used to pull the capsule free of the rocket should there be a problem. So we're enhancing safety relative to using the abort system. And then I'll show a short clip here of Exploration Flight Test 1 that flew in December from the Kennedy Space Center. And I'll talk a little bit about this flight. So we flew this on a Delta IV Heavy, which is the biggest launch vehicle that's used today in the fleet. Those service module panels actually carry part of the ascent load. Great view of the Earth, 36,000 miles from the Earth at the peak part of the flight. And this was really inspiring. A lot of hard work went into this test flight. Again, a great view of the Earth. That is something that was unusual for me as a flight director. Entry took about 45 minutes to get to the landing site and shuttle, and it takes about 7 minutes to get from entry interface to that point. So the vehicle is just sort of flying phenomenally. And here's a splashdown off the coast of San Clemente Island. And then the capsule in the water. The one problem we did have is we were supposed to have those little bags. We had a few of them that didn't inflate. There's 2 that inflated, and we had 3 others that didn't. So that was the major failure, I would say, in the test. But otherwise, a phenomenal test of this hardware. And so we're very excited about that moving forward. There was a lot of interest from the public. We had tons of followers on the internet. At the Kennedy Space Center, the press site was a buzz. It was a little bit like the Apollo and into the shuttle timeframe in terms of interest in that flight. And then relative to Orion, we've started preparing the crew for the flight. Here's 2 test subjects in a vacuum chamber with the suits that they'll use. These are derivatives of the shuttle. Everybody's probably seen the astronauts walk out into the shuttle with these launch and entry suits. It's a pressure suit that protects the crew from the vacuum of space should there be a problem. These 2 test subjects are in a vacuum chamber, and they are at vacuum. And so this test, it's a hazardous test that we do quite frequently at JSC, was testing the 2 suits working with there's like a suit loop, so the two crew members are sort of connected, and so the gases, as the crew exhales, come out and into the Orion life support system, and this was an integrated test of the suit and the life support system in a vacuum at JSC. We did a total of 3 or 4 tests, and so again, beginning to make real progress for Orion. So just this gives you a little bit of a sense of the kinds of things going on across NASA. And now I'm going to transition and talk about the Asteroid Redirect Mission. So this mission came about a little over 2 years ago as we were starting to study what kind of early missions we could do with Orion and SLS. We started to look at the different hardware that we were building with Orion. We had some suit development work. We had something called solar electric propulsion, which is a very efficient system to move objects around in space. We had that work going on. And so as we were looking at these missions, and at the same time, President Obama in 2010 gave NASA a mandate to go to an asteroid by 2025. And so we started to put those things together, and we came up with this Asteroid Redirect Mission, which we recently got to what we would call in NASA the formulation phase. So we've started formally working on the mission. And we really have 2 objectives. It's to do a human mission to an asteroid in the mid-2020s so that we can explore that asteroid and really as a pathfinder or a precursor to Mars. And then the demonstration of solar electric propulsion, which is a technology which I'll talk about that will help us move objects out to Mars in the future in a more efficient manner. So those are the 2 main objectives. Also, the objectives are continue to look for all asteroids as they approach the Earth. That's something that NASA has been mandated by Congress to do, and it's generally a good thing to look for potentially hazardous objects coming your way. And then demonstrate a little bit of planetary protection. And I'll show you a little animation of the mission, if we can get this to play, which hopefully we can do that. Maybe not. Here we go. And I'll sort of talk through it. It's about a 5-minute animation. I think it probably gives the best overview of the mission. So we would launch this robotic spacecraft either on the Space Launch System or a Delta IV Heavy. It would take a couple of years to travel out to an asteroid. And then we have these landing legs that would deploy, and then these 2 robotic arms that we'll use to grab a boulder off of a big asteroid. We'll spend a little bit of time surveying the asteroid. We're looking for the right size boulder to bring back. It's a pretty big spacecraft. So we'll probably spend, a month or 2 flying around this is the operation where we'll fly down over the boulder. And this work is being done at the Jet Propulsion Lab and at the Langley Research Center and at the Glenn Research Center. So we would fly down, and asteroid doesn't have much gravity, so it's not like landing on the moon. It's a little bit more like docking. We would use these micro-spline grippers to grab a hold of the asteroid. It's a series of sharp metal objects that kind of dig into the surface and can provide quite a bit of force. And we're testing this technology at the Jet Propulsion Laboratory and at the Goddard Space Flight Center as well. So we push off from the surface to start moving away. Remember, the gravity is very low here, so it's easy to push off. We would retract the boulder up to the spacecraft. It looks a little bit like science fiction, but Kepler, believe me, and Newton will tell you that this will work. And then we'll bring it to a point where we can do a planetary defense demonstration. So if you remember from your physics, every object tugs on every other object. And so we'll fly around in this halo orbit around the boulder and actually let the spacecraft with the mass of the boulder tug on the asteroid a little bit. And it'll actually change its orbit, and we can measure that. And so we slowly deflect it. After that, we're going to send the vehicle to cislunar space so that we can rendezvous with it in Orion. The launch date would be in about December of 2020 for the robotic mission. And we'll study the boulder a little bit more on the way back. Of course, mission control will be involved. That's where I worked for part of my career. I'd have to have that in the slide. So we'll go back to the stable orbit about the moon. We chose this orbit because it's easy to get into for the robotic spacecraft and also easy to get to with Orion. So here's the astronauts launching from the Kennedy Space Center aboard the Space Launch System in Orion. Hopefully we don't have to throw any switches during ascent, but if you do, the crew will be well trained. Here's Orion traveling out to meet with the robotic spacecraft. And they would dock much like we docked the shuttle to the space station. And then unlike shuttle, there won't be a tunnel for the crew to go into this. That's a bunch of propellant, and we'll talk about that a little later. But the crew would then depress Orion and come out the hatch. And that's how they would do EVAs using the launch and entry suits that we've done testing for. They would crawl across using handrails, just like on the International Space Station. We have a couple booms they'll set up as a work site. And then they'll go to work collecting the samples. It's a little Star Trek-ish looking, that sample container. And then we'll bring the samples back in the Orion spacecraft. So they're living in Orion, they're working in Orion. Orion will be the vehicle that they use for an airlock, and then we'll head back to Earth and Orion. And much like on the FT-1, come back to the atmosphere and deploy the parachutes and for a safe landing in the Pacific Ocean. Which will kind of remind us of Apollo when we fly this kind of flight, I think. I think there'll be a lot of excitement relative to going to... Humans have never visited an asteroid before, and so this mission is pretty exciting. So how do we look for asteroids? Today we look for them from the ground. We use telescopes like this NASA Infrared Telescope facility. We've improved the optics and kind of focused a little bit more on looking for asteroids from a series of these telescopes. We also use radar to characterize them. This is the Arecibo Observatory in Puerto Rico and the Goldstone Radar in California. When we find an asteroid that we might like as a target, we'll bring up the radars and get a little bit more data. We're looking for boulders on the surface. There's a lot of data that suggests most asteroids have boulders. We've also used the Spitzer Space Telescope to image a few asteroids. It's in its cool down phase, but it can characterize the asteroids. And so we've really sort of enhanced the search for asteroids over the last few years. We have a few targets for the mission. The leading reference target is what we call 2008 EV5. That's this asteroid here. It came by the Earth in 2008, and when you see an asteroid name, that's 2008 is the year that the asteroid was discovered. We haven't flown a spacecraft to it, but we know with radar it has boulders on it, much like Itokawa. This is an asteroid that the Japanese flew a spacecraft called Hayabusa 1 in 2005 to this asteroid and actually brought a sample back robotically. And so you can see boulders on the surface, and that's how we're pretty confident that we can actually see boulders on those other asteroids. This asteroid is what's called a carbonaceous asteroid. There are different types. There's stony, but this is a very interesting asteroid because it contains, it's thought to contain water and minerals. And when you think about future space exploration, today we carry everything with us to the space station. We carry water, we carry supplies, clothing. So if you think about long-term exploration, much like explorers that moved from the East Coast to the West in America, they didn't carry everything with them. And so starting to break that bond with Earth, starting to use water from the asteroids, starting to eventually use those minerals is important. And there's also companies actually interested in mining asteroids. And so that's why we eventually down-selected to this carbonaceous asteroid. We'll keep looking for other targets between now and the launch, and we'll select, maybe a year prior to launch, we'll select the actual target. So this is kind of what the spacecraft looked like. I think the animation did a really good job. 2 big solar arrays, and that's the purpose of those is to provide about 50 kilowatts of power. For reference, your air conditioner, if you've got a 2.5-ton unit, uses about, let's say, 3.5 kilowatts of power. So this is a pretty big system. It's required to use the Hall thruster technology to push the spacecraft around and also to push the asteroid. And so this is the launch configuration. You can kind of see with the legs furled up, have a high gain antenna to talk back to Earth, and I'll show a couple other views of the spacecraft. And then looking closely at the base, the business end of the spacecraft, where we'll grab the boulder. We've got a rendezvous sensor system where we'll use a LiDAR to actually characterize the range and range rate. We have a couple cameras that will help characterize the definition of the asteroid. And then, of course, the landing legs that we talked about, and then the 2 robotic arms to grab the asteroid. And then the spacecraft itself is really composed of big propellant tanks of xenon. This spacecraft will have about 10 tons of xenon on board. And as I said before, it'll have about 50 kilowatts of power at the start. At the end of the mission, it'll have 40 kilowatts for the solar electric propulsion system. And then it'll go within a 5-meter fairing. And so the important part of this is we see this system as feeding forward to Mars, so we can push objects out to the Mars system. We can push habitats out. We can push propellant out to Mars. It's extensible up to 190 kilowatts of power, and a lot more xenon, up to 16 metric tons of xenon. So this is sort of how the mission would unfurl. We would launch on the Delta IV Heavy Ore Space Launch System. We would SEP out to this near-Earth object, to the asteroid. We'd spend 120 days to 150 days looking at it. Eventually, we'd go down to the surface and grab it, fly out and do this gravity tractor operation, and bring it back to the distant retrograde orbit, where we'll go visit with Orion. This just shows the characterization phase of how we'll go fly around the asteroid. I think the video did a pretty good job of this, and how we'll go execute that. The timeline, the total stay time might be 300 days or so at the asteroid with the planetary defense demonstration. And so we've spent a lot of time over the last year studying this mission and doing prototypes of the hardware. If you kind of look, you can see we spent a lot of time looking for boulders. We've had a couple fly by the Earth recently in the last year, and we've been able to see boulders. We've done testing with that microspline gripper. This is a boulder simulation with the landing legs around the boulder at Langley Research Center. We've tested these solar arrays up at the Glenn Research Center in a vacuum chamber to make sure they'll unfurl and the power works. We've done docking system testing in Houston and worked on the spacesuits also in Houston, and I'll talk more about those. Then for the crewed mission, and this is the part that I've led. To me, it's a very exciting mission. We would launch on the SLS. We would fly out. It would take about 9 days to get out. We'll fly by the moon at about 100 kilometers, which will be a very exciting maneuver. That slings us out into the distant retrograde orbit. And we'll spend about 5 days there. It'll take about a day to rendezvous, and then 2 days for the spacewalks, and with a day in between for rest for the crew. And then we would come home. We would do a departure burn, and then fly past the moon again. Take about 11 days to come back to the Earth. And we would do 2 4-hour EVAs using a couple of spacesuits that we have adapted from shuttle. The legacy of these suits is actually from Gemini. We've used them for shuttle, for launch and entry, and we'll modify those for the mission to be used in space as well. This just sort of shows a little bit of the considerations we've had to utilize to build the spacecraft. It has handrails for the crew. We've got a couple places we can put the boom, a toolbox to carry tools. The spacecraft will be safe for the crew. We'll be able to transfer power and data. We also see this spacecraft as kind of a building block for future spacecraft to come up with a habitat, perhaps. It has a lot of power we can use, and so for us in the human spaceflight world, transferring that power and data through the docking system to Orion and other spacecraft is very important. So you can see Orion docking to the vehicle. And then this is something that we've been involved in Houston quite a bit, is adapting the launch and entry suit from Space Shuttle to be used. This suit is a derivative of the one we use for shuttle. We've added these gloves. These are the same gloves we use today on the space station to do spacewalks. So we put an adapter on the suit. The boots are exactly the same as we use in the current suit. And we've been doing lots of testing, body positioning, using a device to position the crew member. This is the same device we use on the space station. We've added a mocked-up portable life support system. and then looked at various tasks that the crew can do. We've done a total of 13 runs in the Neutral Buoyancy Lab. We use this big water tank to do our spacewalk simulations. It's a great way for the crew to be what we call neutrally buoyant. So in the space environment, it mimics what they would be like. And the crews say that it's very good training for spacewalks. And then we've done a lot of different tasks of how you would extract samples. This is a little chisel tool. We thought we might have to cut through a bag when we had a different concept, so we did some of that testing in the NBL. We actually did an end-to-end timeline in this suit. We were a little worried about the crew working in the suit. It's not optimized for work like the suit we use on the space station. But the crew's been able to do all the tasks that we've needed them to do. And so we feel confident with modifications, we think this suit could be used. And then I'll talk a little bit about the SEP system. So today, we're in the range of Deep Space One. You had maybe a 3 kilowatt SEP system. Dawn is about 10. Today, for Mars, we think we need in this order of 150 to 300 kilowatts. So this ARM vehicle scales up nicely. The SEP system is very efficient. If you look, compare it to the shuttle engine's generated a lot of thrust. It had to lift the vehicle off the launch pad. Once you're in space, you don't need all that thrust. So the same system, 300 kilowatts, would use about 32,000 kilograms of prop. The shuttle would use about 835 kilograms. So it's a very efficient engine. Just the thrust is much lower. This thrust, this was on the order of 450,000 pounds of thrust. These are very, very small thrust engines, but they're very, very efficient. And so it basically ionizes a xenon propellant and puts it out the back and pushes the spacecraft along in space. This just sort of shows how we can evolve the spacecraft, starting with Block 1 for the Asteroid Redirect Mission. With about 10 tons of xenon, we can move out to this hybrid system that'll help us push systems out to the Mars vicinity. And then this is just a way we're looking, what the Asteroid Redirect Mission has done for us is we look at Mars differently, where we could literally pre-position. We could take 2 or 3 years to send clothing or propellant that we need later on. We could send that to the Mars system. We could launch the crew out of this distant retrograde orbit and then return, in a 6 to 9 month journey back to Earth. So we were thinking about Mars differently because of the Asteroid Redirect Mission. Because the SEP technology, the solar electric propulsion, allows us to push large objects out, just like the asteroid. We can use that to take things out to the Mars system. And then finally, when you think about it, the mission is a great mission for us. We see it as a great way to build the technology required for Mars. We get a great test of Orion, a test of the spacesuits in EVA. We test out rendezvous techniques in deep space. We use these big solar arrays to generate the thrust required with the power system. And then we learn a lot about operations in deep space, the trajectory of maneuvers required, the navigation required. So we really do see this as a building block for Mars. And that's why NASA's currently pursuing this mission. And I think I will stop now and let you guys ask questions. We do see this as a wave of the future. Human with the Earth in the rearview mirror, the Moon and Mars in the distance, and you can see the space station right there. So, thank you.
And if you have a question, raise your hand. I'll come by with a microphone. And for those watching via live stream, type your question in. I'll read it and ask Steve. Yes, sir. Just hold the microphone close to your mouth.
Thank you very much. That was wonderful. So the question I have is, you didn't talk too much about redirecting. So if one of these is heading straight for us, how are you going to redirect it?
Yeah, that's a good question. So the gravity tractor works when I talked. For a big asteroid, the spacecraft that we're building, we could fly near that, and there's lots of theories on how to redirect a big asteroid, and those theories involve things like you see in the movies, from a kinetic impactor to pushing on that asteroid. So this idea of this halo planetary defense demo sort of demonstrates we can get there, and with a large object, use the gravity of that object. All objects in space attract each other, so even the small mass. So if you're there way ahead of time, you can change the orbit of that asteroid, even though it has a lot more mass. So that's one technique we're looking at. And then the spacecraft itself is sort of a building block for other spacecraft that if we had a big one coming toward Earth, we could then use that same kind of approach. Use SEP to get out there, and then either gravity tractor, kinetic impactor. We just have to know it's coming a little bit ahead of time.
I was wondering about how much oxygen the astronauts need for long mission. I was crunching some numbers and thinking, wow, that's a lot of oxygen to carry. Do they use any chemistry to get oxygen out of the CO2, or do they have to carry all that oxygen? Or?
Yeah, for Orion sized today for 21 days for 4 crew members. This mission would be about 26 days. And so it could sustain 2 crew members easily for that time. And I didn't show a lot of the other hardware we'll bring along, but we'll bring an air tank along to do the repress of the cabin. So we've done the calculations for oxygen, and we've got margin.
Okay, but what about a Mars mission?
Oh, Mars, yeah. Definitely for Mars, though that transit time takes a long time. We would have to carry quite a bit of oxygen and maybe extract a little of the oxygen from the CO2. On the surface of Mars, we're flying, how many people are familiar with Curiosity? Good, quite a few. On the next rover, called Mars 2020, we're flying an experiment called MOXIE, and it's literally going to look at, can we extract oxygen from the carbon dioxide on Mars and store that oxygen? So if you think about Mars, oxygen is a great, lots of things you can do with the oxygen. Obviously, for spacewalks, for the crew to breathe, and for propellant as well. And so we're doing that experiment on Mars 2020 to see if literally, because we call it ISRU, in situ resource utilization. So for Mars, we know we have to carry, we can't just carry everything with us. And so that's the theory on Mars, is go ahead and extract oxygen out of that CO2 environment. There's a lot of oxygen there, we just have to free it up.
You were showing at the beginning, when the group was on the space station, the water recycling system, and using all sorts of things that you have up there. And I was wondering, why couldn't things like that be happening in California?
They're looking at some of those kinds of techniques. I mean, essentially what we do is take the urine and we break it down with an acid to take the solids out, turn it into water, heat it up, and then distill it. And so lots of countries use desalination plants, which is a similar kind of technology. So you're right. I mean, I think I'm from Texas as well, and we're doing a lot better this year relative to rainfall. In fact, it rained 4 inches in like an hour in Houston recently. But I think states like California are going to have to start looking at technologies like that to reclaim the water. Water will become a very precious commodity in California.
I don't know if I remember correctly, but the OSIRIS-REx mission, I think it's going to Bennu also. And I was wondering the comparison of the timelines between the capture and the OSIRIS-REx mission taking its sample of a few ounces.
Yeah, OSIRIS-REx, I think it's launching in 2018, going to Bennu. If I keep going back, I do have a slide on that. It had OSIRIS-REx on there. Just give me 1 second. Oops. Yeah, OSIRIS-REx is flying to Bennu in 2018, and it will bring a sample back. It just won't bring as big a sample back. So we're really looking to sort of pioneer bringing large samples back. And a lot of the mining companies, there really are companies that are looking at mining asteroids because they think there's a lot of money to be made somewhere in the future relative to platinum and other very valuable minerals. So yeah, OSIRIS-REx is going to fly. It's a NASA mission managed by Goddard Space Flight Center. And those samples, by the way, will come back to Houston. We do all the curation in Houston for all the samples, so they'll come back to Houston.
Steve, you have a question here on your right.
Yes, Great Britain a year ago landed a exploratory satellite on a comet. They had some difficulty with the landing They tried to use anchors, if you will, to attach their lander to the surface. It failed, and because of the low gravity, the satellite pretty much bounced across the surface, ended up at an angle, and the solar arrays were unable to power the satellite. How does your landing system differ from theirs, and why do you feel yours is going to be more successful?
Very good question. So that mission, I applaud them for what they were trying to do, because it was very tough to land on a comet. What they did is they essentially got to some point, some distance away, and then aimed for the comet without any thrusters to control the range and range rate as they got closer and closer. We'll go ahead and control our range and range rate as we move down, and then we'll actually kind of thrust down into the surface of the asteroid when we get there. So we can thrust down and kind of hold our position and try to make sure we're solidly anchored. But again, it was interesting data to us. Unknown if the comet material is going to be the same as the asteroid. Maybe the comet was a little harder, but that mission was very bold as well. And we think we'll be able to control our descent We'll have a laser ranger, essentially a LiDAR, measuring the range to the surface, and we'll control that range and range rate. It's just like docking. When we bring two spacecraft together, we control that range and range rate. For shuttle, we used to dock at 0.08 feet per second. I'd have to compute that into miles per hour, but very, very slowly. So that's the same technique we'll use.
Steve, back in the back of the room.
How many can I ask? I have two questions, I guess. Why are you redesigning spacesuits, not using the ones that are used on the space station now? And, closer. The lunar explorers and the Mars explorers have found different kinds of rocks in different places. Will your boulder collector do any surveying, or will you just grab the first rock you find?
Very good questions. The reason we're using this launch entry suit instead of the suits we're using on the space station, since we're using Orion only for the mission, we can't carry the weight of those suits in terms of the volume. And so we want to use the same, just like Apollo. The Apollo suits that they used for launch and entry were the exact same suits they used for the spacewalk. So we're using that same kind of approach. We'll have to put a thermal micrometeoroid garment on the outside, but that won't be a problem. So we're using that same approach as Apollo. And then in terms of samples, we hope to, as we fly around the asteroid, we hope to characterize the asteroid pretty well, and so we'll know maybe where to go get the samples and which boulder to go after. So hopefully we'll be able to that precursor data will help us, the Orion mission is launching several years later, so we should have time to analyze that data and find the best samples for the science.
Steve, we're going to stay in the back of the room.
Okay?
Hi. Usually when asteroids enter the Earth, they go through the atmosphere and they're heated to very high temperatures. Bringing them in a little suitcase won't have that heat. Is there any chance that some life form might be introduced to the planet that way?
Yeah, that's a good question. We have scientists that do what they call planetary protection, and so they analyze every object that we're going to go to. And for asteroids, they're pretty confident there's no hazardous life that we're going to bring back. So they would give us unrestricted access to the samples right now based on asteroids. They're exposed to radiation over a long, long period of time, and so the thought is there's no chance of any biological activity. Mars is a different story. There's a lot of debate relative to Mars and bringing samples back from Mars relative to planetary protection, because we know Mars was wet at one time. We know Mars had water. Could a form of life existed on Mars? That's why we're going to Mars with the rovers.
Okay, one more back here.
Okay, you kind of just answered it in a way, but mine was just more about what NASA's primary mission with going to Mars. You see SpaceX and Elon Musk from the start coming out and saying, we want to go to Mars. Well, Elon Musk has always wanted to go to Mars. He wants to start his colony. He wants to terraform it and turn it into basically another world where people can exist to live. Does NASA see a similar future for Mars, or is it more just research about what the planet has?
Yeah, that's a good question. I see us going to Mars and establishing a base there of some sort is kind of what I see NASA doing in the future at some point. much like Antarctica, where we have a permanent presence there, and we can bring crews back and forth. Whether we'll colonize Mars like we have different places, on the planet, that may happen someday. The question is the time scale in my mind, when will that happen? But I'm pretty confident humans will be on Mars at some point. Will Elon be there first or NASA? I don't know. We don't really see that as a competition. We like to work with SpaceX. They're a great company. They're very innovative. We learn from them. They learn from us. I think we have a great relationship with SpaceX.
What do you think the difference, what are you expecting to find in the difference between these asteroids that are out there existing already versus the ones that have already, the meteors that have landed here? Why is that different, or how is it, what's the purpose of just going and getting one when they've already crash landed here before?
It's a good question. It turns out most of the meteors that end up back here on Earth, because they survive the atmosphere, are stony. They're rocks. The asteroids that we're interested in here are the carbonaceous variety, which are a little bit different consistency, a little bit different mineralogy, and that's why we're interested in going to this particular asteroid. The stony ones, like you said, they come back to Earth. We find lots of meteorites in Antarctica. We actually find Mars meteorites in Antarctica. In fact, just in April, there was a big batch brought back. We go to Antarctica and do expeditions in the Antarctic summertime, bring those back to Houston. And so it's a little different. The rocks survive, the ones that are carbonaceous wouldn't typically survive re-entry.
Steve, over here on your left.
Okay.
Hi there. You said the current plans for the International Space Station are to expand it from 6 crew members to 7. I'm wondering if you could talk a little bit more about the extended future of the International Space Station and where they're going with that.
Okay, good question. So space station recently, in our government, we've extended our life of the space station to 2024. So we know it's going to be in orbit at least till 2024. The other partner countries are working with their governments to get that agreement relative to extended to 2024. For the long term, space station might be a place to be turned over to a commercial entity someday. But we really want to keep space station in orbit as long as possible. We think we're learning a lot, and at some point it will wear out, and we'll have to move on. But today we're getting a lot of great research. It's a great laboratory. Lots of medical equipment on board to understand the body. When we go to Mars, we will have medical equipment, but maybe not as extensive. The laboratory on space station, at least initially on Mars, maybe not as extensive. So it's a great place to study lots of things, lots of basic research. And the companies are starting to get interested in it from a drug perspective as well, the pharmaceutical research.
All right, we have time for one more question, and we've been live streaming for a few months now, and we have our first live stream question.
Is that a good thing?
That's a very good thing. And Angela, and I'm not sure where Angela's from, but I think I know. Angela would like to know, other than NASA, are other countries working on similar technology, and will it be like the 60s, like the 60s race to the moon? Will there be a race to Mars?
Yeah, it's, the space station partnership has been, I think it's just been great for the planet. I mean, if you think back to the last 14 years, having Americans and Russians and Japanese and European astronauts all living together in space, it kind of brings the world together. And if you think about going to Mars, if you look at all the countries' economies and how they're faring in the world, I personally don't think it'll be one country racing another. I think times have changed. I think business today is more global. The economies of all the countries are very intertwined. You have an economic problem in Europe and it affects the United States. Economic problem in Japan, vice versa. So I really think it'll be an international partnership going to Mars. It won't be this space race of the 60s. That was a different time and a different era, and there's lots of cooperation back and forth. The Russians have been a tremendous partner. We've learned from them. They've learned from us. We share experiments back and forth between modules. We share this one-year increment, we're sharing the scientific data from that one-year increment with our partners. So I really think exploration is now global, and we're going to do it, with other countries versus the space race of the 60s.
That's a very nice, positive way to conclude our lecture tonight and our lecture series. Thank you. And thank you for attending tonight's event, and we hope to see you at future library programs. Thank you and good night.
And I'll be around if there's other questions for a little while. I'll hang out.